Good morning. Welcome to class. It is May 13th. So, as you should know, your AP test is tomorrow at 3 p.m., right? So, your test is going to be tomorrow at 3 p.m. Let's put this up. Unless you're in a different time zone. So, if for whatever reason you're watching this and you're outside of the time zone, I know a few people were in different states for whatever reason. Uh, but yeah, the test is going to be tomorrow at 3 p.m. You should get an email from College Board. Check the email that you provided for College Board. So the email that you put into your College Board uh, profile, you should get an email from there. You at least need to know your AP ID. So if you don't know your AP ID by now, you need to figure that out. You need to either find it or you need to email me and I can give you your AP ID, just something to figure it out. Um, you should get that. They're trying to get you to log in half an hour before the test. They want you to log in by 2:30. So that's going to happen. Make sure you know your demo, like you've gone through the College Board demo, you know how you're going to submit answers. Again, if you're planning on taking a picture of your answers, then I would suggest taking the test through either your phone or an iPad, or if you're going to be on a computer, that computer needs to be directly connected to some sort of camera. One thing, if you're taking a picture with your iPad, you have to make sure you're not taking a live picture. You have to take it off of the live picture setting and put it onto a normal picture setting. So things like that. And then if you are going to type up your response and then either upload that document or copy and paste it, then you should obviously take the test on your computer. So yeah, those are the options. Um, so yeah, just please reach out to me if you can't log in for whatever reason. And I know a lot of you are stressed. Just try to relax. Um, just the fact that you've worked this hard and got here so far, I'm already proud of you. You're not going to disappoint me. So just do your best, and your best is okay. But yeah, I'm just really glad I had a chance to teach you this year, and it's been a good year. So I'm happy that all of you are in here, no matter how you do. So try not to worry too much about that. Um, so we're going to get into questions now. So if you have any questions, just post those right here. So a few questions I got were about rotational inertia, how we get the rotational inertia. Right. So again, the whole goal is trying to get a kind of cheat sheet where you go through. I would suggest either half a page to a page for each topic. I went through that on the 12th, so yesterday, Wednesday. So look at that video if you need to see where we're at and the different topics. So 1D kinematics, 2D kinematics, forces, momentum and impulse, work, power, energy, circular motion in orbits. Yeah, simple harmonic motion, so springs and pendulums, and then finally rotational motion. So look through those. That's what we're trying to get to. So rotational inertia or moment of inertia, like we saw, is going to be some number times mass times radius squared. Now, you're never going to have to actually calculate the moment of inertia. You need calculus to be able to do that. So all you need to know is it's going to be some number times mass times radius squared. If you need the number, they're going to give it to you. So all we need to know about rotational inertia is it's proportional to mass and radius squared. So bigger mass is going to be harder to accelerate or harder to speed up its turning motion. And the further we put the mass away from the radius, the harder it is going to be to turn. So, and the radius is going to have a bigger effect. So putting the mass far away and trying to turn it, saying attach it far away from our pivot, is going to make it really hard to turn comparatively. So all you need to know is it's proportional to mr squared. You don't need to know the actual number. And in fact, you're probably not even going to be given the number because this year's test is uh, not going to have math like that. Then we have the universal gravitational potential energy. So that's a good thing to look at. So our two different potential energies. We have our gravitational potential energy of mass times acceleration due to gravity times height. And this is useful near the surface of the Earth, or any planet we're on, or moon. Say if we put something near the surface of the moon, we would just use G as 1.6 meters per second squared or something like that. Now, this equation breaks down. It's only an approximation for near the surface of the Earth. Our other equation for gravitational potential energy, the universal gravitational potential energy, being negative gravitational constant times mass of the object, mass of the planet, divided by the distance between the centers of the two objects. Right? Anytime we're doing r or distance, it's always from center of one object to center of the other object. So this is always correct. Little asterisk. Like some of these kind of fell on the extreme large scale, like the size of galaxies. So put a little asterisk there. So here we have our gravitational constant. That's at 6.67 times 10 to the negative 11. I always forget the units for this one because it's so weird. Meters cubed per kilogram second squared. All right. And so this is the one we're going to use pretty much any time. Say an object is in space orbiting the Earth. So we have a satellite of mass m orbiting at a distance r from the center of the Earth. This is what we're going to use. Why is this negative gravitational potential energy? What does the negative mean? Yeah, we're trapped. We're stuck in a gravity well. So one way to look at it is we're on Earth. We're kind of stuck on Earth. We need to add energy to escape the Earth. We need to burn rocket fuel in order to move the rocket. We have to add kinetic energy to escape. So this is always going to be negative or zero. So we can see this is divided by r. So we can imagine as r goes to infinity, or as we get to an infinite distance away from the planet, we're going to see our gravitational potential energy is going to go to zero. So pretty much what this is saying is that we always have a negative gravitational potential energy, and we have to get an infinite distance away for this to go to zero. And in reality, you don't have to go an infinite distance away. You just have to go sufficiently far to where the number gets negligible. So like Pluto's pull on Earth is going to be extremely small, and so it might as well have zero gravitational potential energy relative to Pluto or things like that. So yeah, so that's all this is saying. It's always going to be zero or negative. We're always going to be trapped some amount relative to the planet. And then in order to escape that planet or object, we need the total mechanical energy to be greater than or equal to 0 joules. So we need enough kinetic energy to be greater than or equal to that negative gravitational potential energy. So we need to cancel that out. Any other questions? About literally anything throughout the year? Is there a situation where total mechanical energy is not constant? Yes. So total mechanical energy, this is going to be useful energy for motion. Right. So when we're talking about total mechanical energy, we're going to be talking about kinetic energy, right? The thing is already in motion. Or we can talk about types of potential energy that directly convert to motion. So mostly gravitational potential energy of either form, either equation. These are actually the same equation. And then we can also have spring potential energy, right? A spring can store energy. When I release the energy, it can push the thing and make it move. Gravitational potential energy, I can store energy, can make it move. We have other forms of potential energy, like chemical potential energy in a gasoline tank. You can burn that, and that can eventually make an object move, but that's less direct to us here. So we're mostly talking about things that directly can turn things into motion or energy from motion. So the types of energy that don't include, are not in total mechanical energy, are going to be things like thermal energy or heat. This is going to be the big one that takes away. We can also have sound energy. So pretty much anything that will convert to these. And the thing that creates thermal energy is friction. So we have friction takes kinetic energy, right? It's that motion. It takes kinetic energy and it turns it into heat. So mostly it's going to be friction taking away from our total mechanical energy. So friction takes kinetic energy away and turns it into heat. And then we also have that, I think you meant to say inelastic collision or inelastic kids. So yeah, or we can have an inelastic collision. So in an inelastic collision, we're losing kinetic energy is lost to heat and sound. Right, so again, a good example is dropping this tape down. Makes a pretty loud noise. So there's no math with heat or sound on this AP test, on the Physics 1 test, but you do need to know that that's a place that energy can go. So we're not going to do math with heat or sound, but we do know that we can lose energy to heat and sound. And whenever we talk about this, just kind of a thing to say, whenever it talks about where did the energy go, the correct answer is not friction. Friction is not where the energy went. Friction is the thing that does the work. Friction is the thing that takes kinetic energy away and turns it into heat. So friction is the thing that does work, but it's not where the energy goes, right? Just like the collision is not where the energy goes, the collision is just the thing that takes away kinetic energy and turns that energy into heat and sound. All right, so those are when we're losing total mechanical energy. And for this, it's going to be, we lose kinetic energy to net external forces. So let's get to, I'll get to that in a second, Tam. That's a good question. So when we're talking about this net external forces, let's look at different systems. So let's look at this with no friction. And this slides down the ramp. So we can look at two different systems. So let's say this is our mass. So let's say we're looking at just the mass system. And let's say we're looking at the mass Earth system. So this is another big thing that can come up, is the system that we're looking at. If we're looking at the system that's just the mass itself, what types of energy are contributing to the mechanical energy of this mass as it slides down the ramp? So we're just talking about the mass. So the thing about it is just the mass. We're not including the Earth. The Earth is the thing that includes the force of gravity. So when I look at this mass system, I'm only looking at the mass by itself. So force of gravity is an external force. So if I just look at the system that only includes this mass, the gravity is an external force pulling on this object. So when I get my mechanical energy, the total mechanical energy is only going to be the kinetic energy of the block. And we see as the block slides down the ramp, the kinetic energy gets more, right? It speeds up as it moves down the ramp, speeds up. That kinetic energy goes up, so the total mechanical energy goes up. And so we could look at this being an external force. So we can lose, or I guess I shouldn't say lose, we can change kinetic energy due to net external forces. And gravitational potential energy is always relative to other things. Looking back at our equation here, we need two masses to have gravitational potential energy. Even this equation here doesn't look like we're using two masses for acceleration due to gravity, but we can look at this mg is equal to gmm over r squared, right? This is force of gravity equals force of gravity using our two force of gravity equations, divide out mass of the object. This acceleration due to gravity term depends on the mass of the planet. So this acceleration due to gravity depends on the mass of the object. The gravitational potential energy depends on the mass of the object. Acceleration due to gravity depends on the mass of the planet. So even this equation depends on the mass of the object and the planet. So potential energy is always between two objects. So if I just have a system with one object, there is no potential energy to be included there. Now, if I look at the mass in the Earth, now total mechanical energy, well, the mass, this mass can have kinetic energy all by itself. The mass doesn't need any other object to have kinetic energy. So this thing has kinetic energy all by itself. And the mass and the Earth together, now we can have a gravitational potential energy. So I can add in gravitational potential energy. Now we see as this thing goes down the ramp, potential energy goes down, but our kinetic energy goes up. And this, because there's no friction, the total mechanical energy is going to stay constant. So that's a thing that can come up. That's a thing that I actually missed on that College Board released one with Ferris wheel initially, that Tan pointed out that they just said the mass and they didn't include the Earth itself. So a little tricky thing. So no potential energy in the mass system. So if I'm only looking at, say, this eraser, all this eraser can have by itself is kinetic energy. I mean, I guess it can have stored potential energy. If I were to burn this thing, it would actually burn. But yeah, all this can have is the things that are inside the mass itself. So the mass itself can have energy due to motion, but in order to have energy due to it being a certain height, I need to include the Earth, right? The Earth is the thing pulling it down. So it's all about just where I draw my picture for my system. So I can look at this thing itself, and my system is the eraser, and the Earth is outside of my system. So I'm not looking at the Earth as part of my system. So I have to look at that force as an external force. So when the gravity pulls down on the eraser, the gravity is an external force doing work on the eraser. So the eraser itself is gaining energy. But if I include the Earth as part of my system, as this eraser falls down, the Earth actually falls up towards the eraser. A really small amount, but it still does. And those effects end up canceling out. That's an internal force all of a sudden, because I'm looking at the eraser and the Earth. The eraser pulls on the Earth with an equal force that the Earth pulls on the eraser. Just the eraser pulls the Earth up, the Earth pulls the eraser down. All of a sudden, we have balancing forces due to Newton's third law, and they cancel out and they don't do any work overall if I look at that system. So it's all about where we decide to look. All right, is that okay enough there? All right, so let's keep going. So there was a question. So is it true? So Is it true that more moment of inertia means more angular speed? Well, let's kind of put this into other terms. So, does more mass mean more speed? Does having mass by itself make something faster? No, not really. It's kind of not giving enough information in this question. More moment of inertia does not mean more speed, right? These are completely different. Moment of inertia is the resistance to acceleration, right? Mass resists acceleration is mass resists acceleration. Moment of inertia resists angular acceleration. So we can think of it as if I have a mass that's moving with a certain speed, it's going to be harder to accelerate it. So if I have a big mass moving at a speed, it's hard to accelerate. It's going to hold on to that speed for longer. It's going to be harder to stop. A thing with a bigger moment of inertia is going to hold on to that angular speed more tightly. So if a thing is spinning and it has a big moment of inertia, it's going to want to keep spinning. So it's going to spin for longer than something with a small moment of inertia if I apply equal torques. So mass is saying it's hard to speed up or slow down for a bigger mass. Small mass is easy to speed up and slow down. Moment of inertia, it's big moment of inertia, hard to get spinning, and hard to stop it spinning. Uh, okay, so why can two objects with different masses on a ramp reach the ground at the same time? All right, let's look at this. So again, this only works without friction. So we're going to look at two objects on a frictionless ramp. And they're going to be equal angles. So let's say we put a mass m here, and then we also have another frictionless ramp, same angle theta here, and this is going to be mass 2m. All right, so we have our normal force perpendicular to the surface, and this normal force has to be drawn bigger. 2, 1, we'll call this 1m, 2m. All right, and then we have the amount of weight down the ramp. Sine slides down the ramp, right? Sine slides down the ramp. So I have 2mg sine of the angle. 2mg is the weight, sine of the angle. Sine slides down the ramp. And then we have here, we have mg sine theta. So that means cosine is into the ramp. So mg cosine theta. These two forces balance out. This one is going to be 2mg cosine theta. These two balance out. So when we're looking at this, the balance forces do not contribute to my net force, right? These do not help my mass accelerate down the ramp. So let's apply Newton's second law to these. So net force is equal to mass times acceleration. Well, the net force on this mass is going to be mg sine theta is equal to, we have a mass of 1m times acceleration. So mass divides out. So my acceleration is going to be acceleration due to gravity times sine of the angle. Now let's look at this one. Same thing, Newton's second law, net force equals mass times acceleration. Ran out of blood. So we have now 2 mg sine theta. That might be looking bad. This looks like it should be twice as much. But what is my mass here? My mass isn't m, my mass is 2m times acceleration. So divide both sides by 2m, so my acceleration is going to be acceleration due to gravity times sine of the angle. So that's kind of mathematically what's happening. So what's kind of happening with our Newton's second law, we can see here, this 2m does get pulled harder, right? The 2m gets pulled with a bigger force. So the force is bigger, but mass resists acceleration. So this one gets pulled harder, but the 2m is harder to move. So it gets pulled harder and it's harder to move. Those effects balance out to give me the same acceleration. Mass m gets pulled with less force, but it's a smaller mass, so it's easier to move. So I pull a smaller mass with a smaller force, and it ends up moving the same as pulling a bigger mass with a bigger force. And so both of these will reach the floor at the same time, as long as the angles are the same and the surface is frictionless. We're going to run into more problems that there's friction. But yeah. Good question. A cart with no friction reaches the ground before a sphere. All right, let's look at this again. We talked about this a little last class. So we have a cart without friction. So a lot of times you'll read this. It's not the cart that has no friction. We have frictionless bearings is a lot of times what you'll see. So we have frictionless bearings, or frictionless, the wheels have no friction with the axle. Something like that is a word that you'll hear. So no friction with the axle. And a lot of times what they'll say is that the wheels have negligible mass, negligible / small mass. So a lot of times what they're doing here, frictionless bearings, wheels have negligible or small mass, they're pretty much saying ignore rotational motion of the wheels. All of that is getting together to say ignore the moment of inertia of the wheels and the torque provided by the wheels. So the whole point of this is we're pretty much completely ignoring it. It's almost like this mass just slides down the ramp without friction. And so when we do that, we're going to see that we have just, for this one, we have gravitational potential energy turning directly into that translational kinetic energy. So all of the potential energy is going into moving the cart down the ramp. And frictionless bearings, really small wheels, negligible mass wheels, none of the energy is going into turning the wheels, or none of the energy is going into friction. Then we have an object rolling down the hill, a sphere, cylinder, it doesn't really matter. Here there is friction, again, as long as there's no slip. There's no slip, then there's no work done by force of friction, right? I need a sliding between the surfaces for there to be a force of friction. So if the object doesn't slide when it rolls, if it doesn't slip, then there is no work done by friction. So here we see we start with gravitational potential energy. Let's say we same mass, same height as before. So they both start with the same gravitational potential energy. But here, some of the energy goes into making this slide down the ramp this way, but part of the energy goes into rotating this thing. So here, because energy goes into rolling the object, there's less energy left over to make it go in a straight line down. So energy is getting taken up to make this thing roll, less energy is left over to make the thing move down the ramp. All right, so that's a moment of inertia question. So let's look at this. So let's say these both start at the same height initial, and angle theta, right? Or angle theta is right here. pretend those ramps are the same. Good enough. All right, so let's say we have then hoop. And we'll say this is mass M. And then we have a solid cylinder, a solid disc. Also of mass M. All right, so we have these two objects that are going to roll down the ramp. Now, we have both of these are starting with gravitational potential energy, and both of these are turning that energy into kinetic energy. Let's say they get all the way down to the bottom of the ramp, so all the kinetic energy goes away. Some of this goes into translational kinetic energy, some of this goes into rotational kinetic energy. All right, so we have gravitational potential energy, mg, h initial. They both have mass m. They both start with the same height, is equal to translational kinetic energy is 1/2 mass times speed squared. And these are the final values, plus 1/2 moment of inertia times the angular speed squared at the end. But then this is where we can get to those different things that you should 100% definitely have written down somewhere, right? The distance traveled tangentially in a circle is going to be equal to that angular distance traveled times radius. Then we have our tangential speed is going to be angular speed times radius, and our tangential acceleration is going to be angular acceleration times radius. You 100% need to have this written down on your sheet. All right, so we have this. Now, angular speed and tangential speed. So the tangential speed of this, however fast the object is going as it rolls, is going to be the same as the tangential speed as long as it's not slipping. So that tangential speed of the surface right here is going to be the same as the speed of the object as long as it's not slipping. So I could say instead of angular speed, tangential speed is angular speed times radius, or angular speed is going to be that tangential speed divided by radius. I'm going to multiply both sides by 2 because I don't like the 2. So 2 mg times the initial height is going to be mass times that final speed squared, plus multiplied both sides by 2, so that I got rid of the 2 there. Moment of inertia. Final angular speed squared is going to be speed squared over radius squared. So then we can get into our moment of inertia question. So the thin hoop, these are the same mass. If all the mass is right here, is this going to be a big or a small moment of inertia if I have a big radius? Again, remember, the only thing you really need to know about moment of inertia, it's going to be some number, some constant, times mass times radius squared. You just really need to know mass times radius squared. If all the mass is at the edge, we have a big radius with the same mass, so what's my moment of inertia? Big or small? Yeah, we're going to have a big moment of inertia. And then here, the radius is evenly distributed. So I have some at a really small radius. I have some at the big radius, but more evenly distributed. I'm going to have a small moment of inertia. So it's going to be easier to spin the thing with the mass evenly distributed. I don't have these memorized off the top of my head. Let's look back. Where did I put those? See, even I don't remember these immediately. So this one is just mr squared. Moment of inertia is mr squared. This one, the solid disk, is, what is that, 2/5? No, that's a sphere. Right, yeah, 1/2 mr squared. So I could do 2 mg h initial is equal to mass times final speed squared plus moment of inertia for the hoop would be mr squared speed final squared over radius squared. Radius divides out. So we even see the radius doesn't matter. So I could even say these are different radii. So a thin hoop that the only thing is different is the radius and you didn't change the mass, that's not even going to have an effect on how fast this thing takes to roll down. We did this in class that one time. So we have this 2 mass times acceleration due to gravity times initial height. mv squared plus mv squared is 2mv squared. Divide out the 2m. Take a square root. So the final speed is going to be the square root of acceleration due to gravity times the initial height. Then I can do this for the cylinder or the disc. Yeah, cylinder is slightly different. So for the disc, we have, again, the same equation, 2 mg times height initial is equal to mass times final speed squared plus, now this is 1/2 mass times radius squared times speed squared over radius squared. Radius squared divides out still. mv squared plus 1/2 mv squared is going to be 3/2 mv squared. Again, radius doesn't even matter. Every single solid disk with a mass m is going to roll at the same speed. It does not matter what the radius is, as long as they're the same. Actually, it doesn't even matter what the mass is. What am I saying? So yeah, it doesn't even matter what the mass is. As long as they're the same geometry, they're going to roll the same. So it doesn't matter what the mass of this hoop is or the radius of the hoop is. As long as they're identical looking hoops, it doesn't matter. A solid disk, as long as they're both solid disks, it doesn't matter what mass I make it or how big or small I make it. It does not matter. I can multiply 2/3 by both sides, so I get 4/3. Acceleration of gravity times initial height equals final speed squared. So here the final speed is going to be the square root of 4/3 acceleration of gravity times initial height. 4/3 is bigger than 1, so this one goes faster. And that's not we didn't even have to go, yeah, mass and radius don't even affect anything. It's pretty crazy. We tested this in class. I don't have a good way of demonstrating this in here. I'm sure there's a video somewhere. The moment of inertia does matter. And moment of inertia, again, the only thing that affects the moment of inertia is the k. And so that's going to be, this k is determined by the distribution of mass. So the only thing that matters is the distribution or geometry. Well, that's a better way of putting it. The only thing that matters is the geometry of the shape. And then we didn't have to go all this way. This was only to kind of prove that mass and radius don't affect the speed. We could have just gotten here and we could have seen, okay, a big moment of inertia. If we have a big moment of inertia, we only have so much potential energy to go around. So if we use up a lot of that energy making this thing roll, that means we have less energy left over to make this thing go sideways down the ramp. So it's going to go down the ramp more slowly. And then the opposite holds. Small moment of inertia, less energy taken up to make this thing roll, more energy left over to make it go down the ramp. This is a really easy question I could ask, and you wouldn't even have to go through any of this math. You just really have to quickly go through. Big moment of inertia takes more energy to roll, less energy left over to make it go down the ramp, it'll go slower. And that's the entire wording you would have to use without actually doing all these calculations. Anything else about these or other things? Is it true okay, so on an incline with just the mass, this is a kind of tricky question because it's not always going to be true necessarily, that statement, as long as it's just sitting on a ramp. So if the object is just on a ramp with no outside forces, no outside influence, then yeah, we are going to see this mass M here, mg sine theta down the ramp, and then yeah, our normal force is just going to be equal to mg cosine theta, and then yeah, we're going to see our normal force is going to be smaller than the weight. But there are things I could do, right? What if someone was pushing down on the ramp, on the object? Could I make the normal force bigger than the weight? Like I have this right here. What if I were to push? Yeah, action, reaction. So if I push harder, so then the paper has to support the weight and my push. So whenever we do that, there can be more. So that's the only reason. When I push it, because I can easily push more than the weight. This thing doesn't weigh very much. I can easily push down more than this thing weighs, right? I can exert more force than the weight of this thing. So anytime you have additional pushes, it's going to be completely different. And then when you're on a ramp like this, here we can see when I hold this up, the normal force only holds up part of the weight. The other part of the weight is being held up by friction. So friction holds up part of the weight, keeping it from sliding down, and normal force holds up the rest of the weight. And so the normal force doesn't hold the entire weight if friction is holding up some of it, unless we're doing something weird like pushing down into this thing. And again, I wouldn't, this is the whole reason I won't say like always or never. I wouldn't put it past College Board to ask something stupid like that where someone's pushing on the object on the surface. What affects the period of a pendulum? All right, good question. So looking at a pendulum, right? So first of all, we're going to look at the simple harmonic motion version of this, not SMH. I almost wrote SMH. SHM. So simple harmonic motion. So again, the simple is small angle, small displacement, delta theta, from the equilibrium position, which is going to be, angle is going to be less than or equal to 10 degrees. And then the harmonic motion, harmonic means it's pulled back to equilibrium. Yeah, if moved away from equilibrium. All right. So when we're looking at this, so things that I can do to affect the period of the pendulum. So period of the pendulum, for this simple harmonic motion approximation, there's a much more fun equation that's a series of terms if you go to greater angles, but it's 2 pi square root of length of the pendulum divided by acceleration due to gravity. So things I can do to affect the period of the pendulum, I could change the length of the string. So if length of the string goes up, we're going to see this is direct square root. This is in the numerator, length goes up. That means the period goes up. So a longer string takes more time to go through. And then if it takes more time, then it's going to be less frequent, right? We can always ask about frequency. Or if the length of the string goes down, it's going to be easier to go through. It's shorter. And so the period is going to go down, right? Numerator, make the numerator. What am I doing? If the length, why did I say length again? I just confused myself. Sorry. Length goes down, period goes down, and then frequency goes up. So if it takes less time, then it's more frequent. And then we could also change the planet we're on, acceleration due to gravity. This is in the denominator, so if I make the denominator bigger, the other number gets smaller, the overall number gets smaller. And it kind of makes sense. If I put this on a planet with a big force of gravity, big acceleration due to gravity, it's going to get pulled down fast and swing really fast. So as the time for the swings go down, it's going to become more frequent, right? Period and frequency are inverses of each other. Then if I say put this on the moon with less acceleration due to gravity, smaller denominator, bigger number, the moon pulls down not as much, so it takes more time to complete motion, and the motion becomes less frequent. All right, so those are the major things that can affect this, at least for small angles. Things that won't affect it are the mass on the pendulum. Then things that we can do that are kind of outside the box changes. So let's say like where the equation fails. So the equation is going to fail if we start getting large angles greater than 10 degrees. Now, if we start getting angles greater than 10 degrees, then that will start affecting the period of the pendulum. If I pull this thing back to like 80 degrees and let go, then I'm going to have an effect of the angle on the period of the pendulum. And then it also fails if there's air resistance. If we have air resistance, then we have a lot of things that come into effect, which would be where the mass would even have an effect on how fast it goes through the air and different things like that. How would you apply angles to the equation? That's a question where to do that, you're not even really going to do that in Physics C. That's more like, so Physics C is the introductory level mechanics class. You would have to go to the sophomore level physics class before you really start doing that. And you need differential equations. So we're not going to do that. It's just a thing to keep in the back of your mind. They're not going to ask you to do math with this to make a new equation or anything like that. But they could ask you a question where it becomes a large angle or something. How I could imagine them asking this is a student is doing a pendulum lab and they pull it back and they show the angles. They do like 10, 20, 30, 40, 50 degrees or something. And they notice that the period of the pendulum is dependent on the angle. Does this make sense? And you would just have to say, oh, yes, it does make sense. This is no longer simple harmonic motion because we're not doing small displacements from equilibrium. So that's all you would really have to do. You're not going to have to do math with it. I really doubt they're going to say for large angles, how does this equation change? They're not going to say that. It would just be like, oh, students notice that at large angles, this happens. And you would just have to know, okay, it becomes non-simple harmonic motion then. All right, back to the previous one. So yeah, it was on this one. So on the thin hoop solid disk, does the thin hoop's angular acceleration less than the solid disk? Yes, this is a smaller, that's one way of looking at it also. So these are going to have the same force of friction pulling up. Actually, they're not going to have the same force of friction. Yeah, angular acceleration is going to be net torque divided by moment of inertia. Well, I'm not going to get into all that. That could get really messy. But yeah, so angular acceleration is net torque divided by moment of inertia. Big moment of inertia, it's in the numerator, is going to be a small acceleration. So yeah, that's another thing we can look at. A big moment of inertia. This one is going to have a smaller angular acceleration, and then in general, just a smaller acceleration. All right. Yeah, of course. I have not gotten the email yet. Did you email it from your Garland ISD account? Oh, there it goes. Did you mean to send it sideways? There we go. All right, so here we have that hungry 700 Newton bear. Are we having a meeting tomorrow? Yeah, tomorrow morning. I'll also, if any of you have to go to another class right now, tomorrow morning I'll also be back at 10. So I can still answer questions. Tomorrow we're just going to do kind of like a mapping of physics where we go through and try to relate concepts. And so it's not going to be really draining. Not going to be like, here's 15 AP test questions right before your test. So yeah, tune into that, and it will be more review, and then show back up with more questions. I like this. The more questions, the better, because I'd rather help you with things that you need help with as opposed to things that I think you need help with. All right, so yeah, if you have to go to another class, have a good day. I'll try not to make the video too long, but yeah, you can watch this after the fact. You can ask me that later today at 1. Also, you can come back to tutoring to ask that. Or tomorrow morning. All right, so we have a hungry 700 Newton bear walks out on a beam in an attempt to retrieve some goodies hanging at the end. The beam weighs 200 newtons and is 6 meters long. The goodies weigh 80 newtons. When the bear is at 1 meter, find the tension on the wire. All right, so we have a few things going on here. So the beam stays at rest, right? At rest. So if the beam stays at rest, this means a few things have to stay balanced, right? So we know our net force has to be 0 newtons because it stays at rest. This does not begin moving up or down. And again, stays being the key word. Stays at rest means the velocity stays 0. If the velocity stays 0, there's no acceleration. If there's no acceleration, there's no net force. So it's not that it's at rest, it's that it stays at rest. The other thing is our net torque has to be 0 Newton meters because it does not begin rotating. All right, so it doesn't begin rotating and it doesn't begin accelerating up or down. So both of these have to be true. Now, looking at this, we can do multiple pivot points. It's probably going to be best to look at the wall as a pivot point. All right, so I have the wall right here. Let's call this my pivot. We can kind of put this wherever we want. This is just going to be an easy spot to put it. We have this wire. We're trying to find the tension here. We have a 60-degree angle. The bear is 700 newtons at 1 meter away. 1 meter. The beam weighs 200 newtons and is 6 meters long. So the entire length is 6 meters. The beam, I think you do that correctly. You have to put this at the center of mass, which is 3 meters from the edge. And that's only 200 newtons. All right, so we're trying to balance our torques. So the torques counterclockwise equal the torques clockwise. So the torques trying to turn this way equal the torques trying to turn this way. So, well, counterclockwise is the tension. So this is going to be the tension. The torque caused by the tension, there we go, is going to be equal to the torque caused by the bear plus the torque caused by the beam, the weight of both of those. torque is going to be radius times force times sine of the angle. So luckily they gave us weights, so they already gave us forces. We don't have to calculate those. So we have the tension is going to be force of tension times 6 meters times sine. The angle is 60 degrees between the tension and the radius. So that'll equal 2. The weight of the bear, 700 newtons at a distance of 1 meter. And then sine 90 is just 1. I'm just going to ignore sine 90 is 1. I'm going to be a little bit lazy here. Plus 200 newtons at 3 meters away. Sine 60, why am I blanking? Sine 60 is the one that's 1/2, right? It happens. No, sine 60 is the square root of 3 over 2. Tension times 6 times square root of 3 over 2 is equal to 700 times 1 is 700. 200 times 3 is 600. 600 plus 700 is 1300 Newton meters. 6 divided by 2 is 3. Tension is equal to 3 square roots of 3 is equal to 1300. Equal to times 3 square roots of 3. Divide both sides by 3 square roots of 3. When you do this, make sure you put that in parentheses. I have a suspicion that might be what happened, maybe. Oh yeah, I missed the goodies. So that's 80 newtons. Sorry about that. Plus 80 newtons at a distance of 6 meters. So 1780. Divided by 3 divided by square root of 3. Yeah, that actually looks closer to it. I was like, that doesn't look like the answer I recall off the top of my head. But yeah, we get tension is 342.6 newtons. Yeah, I don't know what went wrong. It looked like everything was going right. Oh, I know what you did. Yeah, the radius for the tension. Yes. Any other questions? And again, if you need to go somewhere, you can feel free to go somewhere. Yeah, that happens. You just realize the torque equation is it actually is. Yeah, you just multiply it by the yeah. I mean, torque is just going to be the force times the radius. Yeah, that is one way of looking at it, just like the where did I put those? Yeah, really is similar. Yeah, you can almost look at that like a rotational force. Okay, does conservation of momentum apply to interactions between two different objects? What about a system with only one object? All right, so yeah, that's a thing to look at. Do you have to turn in the checklist? Um, no, you mean it's more so do it for yourself. The thing I am checking is on the 5th that you did the one that you were able to get into the College Board website and do the demonstration. That's the thing I'm looking for. But yeah, you should fill out the checklist and make sure you're doing all of those on that. All right, so that's a good question. Let's look at a normal collision between two objects. Let's just say this thing starts at rest. So frictionless. So we have this mass capital M, we have a lowercase mass m. This is moving at speed v. This is at rest. So these things go and they collide. So I have a few ways I can look at this. If I look at both objects together when they collide, so system is going to be mass m and lowercase m. So when they collide, m, I'm looking at this whole thing right here. What can I say about these forces that these masses exert on each other? It's an internal force. So I have the force of mass, the force that lowercase mass exerts on capital mass M. That pushes back that way. The capital M pushes this one this way. Force of mass capital M on lowercase m. These are equal and opposite, right? Newton's third law, equal and opposite forces. Or one way of looking at it is like you said, it's an internal force. So we can look at it that way. And I can look at my impulse equation, right? Impulse is equal to force times time. The only thing about these is that one is negative, right? So let's say that this is to the left, so I'm going to call this negative F. This one's to the right, so I'm going to call this positive F. So I could say change in momentum for this capital M. Well, it has a force of negative F exerted on it for a time t. This one, change in momentum for the lowercase m, it gets pushed to the right, so this is going to be positive force F times time. Now, the collision has to take the same amount of time for both, right? Either both objects touch or neither object touches. It's not possible for one of my fingers to touch the other finger without being touched back, right? So they're either in contact when they collide or they're not in contact. So they have to have the exact same time during the collision. Newton's third law, they have equal and opposite forces. So what I can look at here is this one gains positive momentum. However, positive momentum, this goes up by, this goes down by the same amount. So the overall effect of both of these together is there is no change in total momentum. So thinking of it like saying it in an easy way, however much momentum lowercase m gains is the exact same amount capital M gains. That's not the best way of thinking of it. However much positive momentum, however much the momentum moves in the positive direction for M, the momentum has to move that much in the negative direction for capital M is a more correct way of stating that. But now I could look at just an individual mass. What if I look at the system individually? What if I look at one as the system of capital M only? And then I can look at the system of lowercase m only. Now when I look at each of these masses, now this is no longer an internal force. Now I just have mass capital M over here getting hit with a force, what I called negative F, the force of the small mass on the large mass. And then on this side, completely separated, then I have the small mass gets pushed with an equal force. So the big mass hits the small mass. This is positive F. Now we have the same thing. The change in momentum for M is positive force times time. But I have the change in momentum for the capital M is negative force times time. These two numbers are equal and opposite, but now my systems are completely separated. So this system involving mass M only is going to lose some momentum. Is not the best way of saying it, but we could say lose momentum. And then looking at this system of mass lowercase m only, this is going to gain momentum. So if I was looking at this mass only, momentum is not conserved. If I look at this mass only, momentum is not conserved. But if I look at both masses involved in the collision, then momentum is conserved. And this again is why anytime I talk about something colliding with the earth or a wall or something, so I'm saying the momentum of this roll of tape when it collides with a table, well, I'm not taking into account the earth itself, right? The table is attached to the earth. I'm not accounting for the mass of the earth. So momentum of just this roll of tape is not conserved. I would have to look at the momentum of the roll of tape and the earth it collides with in order to show momentum is conserved. But for each of the individual masses, no, momentum is not conserved. Momentum is transferred between masses, but we need to look at all the masses involved. All right, maybe one more question. I don't want this to go on too long so people will actually watch it. Hopefully these are helpful. Have these been helpful? But these are, we're also getting into some of the more subtle things. Honestly, if you're getting to the point where you're trying to get points for this, you've probably already gotten a lot of points by this time. So you're already doing well if you get to a question that's starting to really get into the details of the system. Those are the points where you're trying to get a 4 or a 5 by that time. Well, if there's no other immediate questions, just keep working on this. Keep trying to make your sheet. Keep trying to do this. Keep trying to put this together in a coherent way. Your cheat sheets, they should be as concise as possible. Really try to get at most one concept per page. So don't go super in depth on those, because if you write too much detail, you're not going to be able to find your work. You don't need to write out all of the equations because you should have them on your formula chart. Yeah, I'm blanking. But yeah, just keep working on these. Keep reviewing. No matter how well you do, I'm going to be okay with it. Just do your best, and I'm happy with how you do. So try not to stress. Try to get some good sleep. Try to get a good breakfast. We'll be back here tomorrow morning, and you need to be able to log in and do the demo for College Board. All right, and if you submit a picture of your cheat sheets, I'm going to count that as bonus points. And if you do the activity tomorrow, I'll count those as bonus points. So keep working on that and have a good rest of your day.